Let's take a look at this example. Please notice that we have given voltage source and we have given current. Please notice that this is peak voltage and we have given peak current. If I have voltage given and total current, I can find Z total. Z total is equal voltage source over I total. My current is not specified that this is total current, but please keep in mind that we are talking about the series circuit, and in series circuit we have just one current, so there is no other option just saying that this is my total current. So I have voltage source is equal 40 volts over I total, which is equal 20 milliamps. Okay, this is equal 2 kiloohms, but our answer is not complete. Why is not complete? Because we have to find also the angle. In order to find the angle, I'm going to use the formula for power factor. Okay, power factor is equal cosine of angle theta, and this is also equal R over Z total. R is given, we found Z total, so we can find very easy angle theta. So if you are going to solve this part of the formula for angle theta, you're supposed to obtain theta is equal inverse cosine, and I have R over Z total. So I have inverse cosine and R is 1 kilo ohm over Z total, which is equal 2 kilo ohms. Everything is equal 60 degrees. Someone is going to say, how come you know if this is positive angle or negative angle? Because some of you can say, oh, this could be negative angle. I have extra information given. X of L is greater than X of C. So when X of L is greater than X of C, it means that I'm going to have positive angle. So right now I can write that Z total is equal 2 kiloohms and angle of 60 degrees. So this is my Z total. Next, we're supposed to find the reactive power at the capacitor. In order to do so, we're supposed to find X of C. We can find X of C by subtracting from Z total resistance. We're supposed to find X of L, and after that we are going to get X of C. But in order to do so, we're supposed to find X of L first. So if X of L is equal J omega L. So I have J times omega, which is equal 6 times 10 to the 6, of course, radians per second, times L, which is equal 500 microhenries. And this is equal 3 kiloohms and angle of 90 degrees. You can write J 3 kiloohms or 3 kiloohms angle of 90 degrees. It means exactly the same. I prefer to work with polar forms, that's why I use angle. Next, I can find X of C. In order to find X of C, I'm going to use the formula which says Z total is equal R plus X of L plus X of C. In order to find X of C, you're supposed to solve this formula for X of C. So X of C is equal Z total minus resistance and minus X of L. I can use this formula because Z total has the angle. If Z total wouldn't have angle, I was supposed to use the Pythagorean theorem. But at this moment, we can use this formula. So I have Z total equals 2 coulombs, an angle of 60 degrees, minus resistance, which is equal 1 coulomb, minus X of L, which is equal 3 coulombs, an angle of 90 degrees. Everything is equal 1.26 kilo ohms, an angle of negative 90 degrees. Okay, so this is the capacitive reactance in my circuit. If I have capacitive reactance in my circuit, I can find very easy the reactive power. So I have QC is equal 1/2, I'm supposed to use 1/2 because I'm using peak value, times IC raised to the second power times X of C. This is equal 1/2, and IC, you're supposed to keep in mind that I total is equal IR, also is equal IL, and this is also equal IC. And in our case, this is equal 20 milliamps, because this is series circuit. That's why I'm going to write over here 20 milliamps raised to the second power times X of C, which is equal 1.26 kilo ohms, an angle of negative 90 degrees. Everything is equal 252 millivolt amp reactive. Okay, so this is the reactive power at the capacitor. Next, I'm supposed to find the total reactance in my circuit. So I'm supposed to write X of T is equal X of L plus X of C, where X of L is equal 3 coulombs, an angle of 90 degrees, plus X of C, which is equal 1.26 kilo ohms, an angle of negative 90 degrees. This is equal 1.74 kilo ohms, an angle of 90 degrees. So this is the total reactance in my circuit. Please notice that we have angle 90 degrees. So it means that the inductor is going to take over the capacitor. Now we can find the total reactive power. So I have a formula which says Q total is equal 1/2 I total squared times X of T. So this is equal 1/2 20 milliamps raised to the second power times X of T we found is equal 1.74 kilo ohms. Everything is equal 348 millivolt ampere reactive. So this is total reactive power in my series RLC circuit. Now we can find power factor. Power factor is equal cosine of angle theta. So I have cosine of angle 60 degrees is equal 0.5. But please notice that angle has positive sign right? That's why I'm going to write word lag Y, because in the inductive circuit, right, because we have the situation where the inductor is going to take over the capacitor, current is going to lag the voltage source by, in this case, 60 degrees, okay? That's why I'm supposed to put word lag next to the power factor. Next, I'm supposed to find the equivalent parallel circuit. How come I know that? Because I have to find the current which goes through the resistor in the parallel circuit and current which goes through the reactance in the parallel circuit. So I'm supposed to simply write Y total. I'm supposed to find the total admittance 1 over Z total. Now I would like to ask you to switch your calculators to rectangular mode. So if you are going to enter these numbers into your calculator and press enter or equal, you're supposed to obtain the answer in rectangular form. So I have Z total 2 kilo ohms and angle of 60 degrees. This is equal 250 microsiemens minus J 433.01 microsiemens, where real part is my conductance and imaginary part is my inductive susceptance. So this is my BL. So in order to find the current which goes through the parallel equivalent circuit, so I'm going to have my resistor and I'm going to have my inductor. So I have my RP and this is my LP and this is my voltage source. So what am I supposed to do? I'm supposed to realize that voltage source is equal to the voltage across the resistor in my parallel circuit, and this is also equal to the voltage across the inductor in my parallel circuit, right? This is parallel circuit, so voltage source is basically across every single component in my parallel diagram. Now we are ready to find the current which goes through resistor RP. So I have formula which says I RP, okay, the current which goes through the resistor in my parallel equivalent circuit is equal voltage source over RP. But someone is going to say, but we don't have RP. Because the problem is not asking me for RP. So basically what I can do, I simply rewrite this as voltage source over 1 times 1 over RP, where 1 over RP is nothing else just conductance. So I can say this is equal voltage source times conductance. So voltage source is equal 40 volts times the conductance, which is equal 250 microsiemens. This is equal 10 milliamps. Okay, so this is the current which goes through the resistor in my parallel equivalent circuit. Next, we're supposed to find the current which goes through the inductor. So we're going to use again Ohm's law. So I have I L P. Before I didn't know what component I'm going to have in my parallel equivalent circuit. That's why problem says I'm supposed to find the current which goes through the reactive component. Right now I have inductor, that's why instead of X I'm going to write L. So I have voltage source. I write voltage source because the voltage across each component is equal to the voltage source. I can write VR over R, VL over L, but I can also write VS over R or VS over L. So divide by XLP. But someone is going to say, we don't have XLP. So what we are going to do is simply write the voltage source over 1 times 1 over XLP. This is nothing else, just the inductive susceptance. Okay, so I'm going to write that this is equal voltage source times BL, which is equal 40 volts times negative J 433.01 microsiemens. This is equal 17.32 milliamps, an angle of negative 90 degrees. So this is the current which will go through the inductor in my parallel equivalent circuit. Now we are ready to find the total reactive power. QP is equal 1/2 VLP, voltage across inductor in my parallel equivalent circuit, raised to the second power, over X of LP. Okay, but we didn't find X of LP, but we found the inductive susceptance. So what I'm going to do, I'm going to simply write that this is equal to 1/2 VLP to the second power over 1 over BL. Okay, if you are going to use algebra, you are going to realize that we have QP equals 1/2 VLP to the second power times BL. And if you are going to plug in the numbers, you are going to have QP equals 1/2 VLP is equal 40 volts raised to the second power times BL 433.01 microsiemens. This is equal 346.4 millivolt ampere reactive. So this is my total reactive power in the parallel equivalent circuit. Now I would like to compare this answer with the total reactive power in my series circuit. We got 348 millivolt ampere reactive. So we can say that this answer is very close to this one. That's why we can say that the problem is solved correctly.